Okay, this is a bit of quick chemistry. It's really aimed at people who take biology A level but perhaps don't do chemistry. To try and just get a few of the terms that we would commonly use and just get you familiar with them. Hopefully a lot of it you will remember from GCSE, but sometimes we go pretty quickly and we pick up on things and maybe the chemists get it and the biologists don't. So just to give you a bit of an idea of some various things. When we're talking about chemicals, we often talk about different groups, and what we're talking about here is things like, for example, CH3, which is called the methyl group. So if we were drawing something out, like, let me just draw this molecule here. Now notice that I'm going to put all the hydrogens in. The way I've drawn this kind of stick diagram, this is actually the chemical ethanol, what we would commonly call alcohol, although it just belongs to the group of chemicals called alcohol. Notice it ends in OL, tells me it's an alcohol. If I was going to write that out as a formula, I could write it and say C2H6 and an oxygen, okay? Because that's literally telling me how many carbons, hydrogens, oxygens in there. This is called an empirical formula. Now, it's not always useful to us. What we often want to do is to think in terms of active groups. So this bit at the end is a methyl group, yep, CH3. So perhaps it's more useful to us to write it like this. At this end, you've got, oh wait, I've even missed out the line between them, haven't I? This is the bit that makes this molecule, if you like, an alcohol. And by separating it out like this, I can now see, yeah, there's a methyl group at this end, and there's an OH on alcohol group at that end. And by splitting out like that, it allows me to see, that bit and that bit are the useful, interesting bits for me. So if I make it a slightly larger molecule, I could continue the process and say, same thing, but if I had an extra carbon and hydrogen group in here. Notice again, I've kept my methyl group at the end. I could, of course, write the same thing out like this, CH3, and use brackets, like in maths. Okay. I could write the whole thing out in this empirical formula, but it's not as useful to me as doing it like this. So methyl groups you'll come across a lot. Also alcohol groups. Now, while we're on the subject of alcohols, do you remember doing alkanes in chemistry, where you had these long chains of carbon and hydrogen? I'm not even going to bother drawing the hydrogens in this time. We don't always draw them. We just assume that they're there. If there's nothing there, we'll assume that it's a hydrogen. Okay. But the way that we name chemicals, or the way the chemists name chemicals, does follow a nice pattern. So, for example, if I do that one is CH3OH is methanol. Okay. If I do the next one, CH2OH, that is, as we've just seen, ethanol, methanol, ethanol. If I keep going, the next one is propanol, and all I'm doing here is I'm adding extra CH2 groups in the middle. Next one up, butanol, pentanol, and you might even begin to recognise these from the alkanes that you did. Just by adding on these groups, so we had methane, ethane, propane, butane, pentane, hexane, heptane, octane, and so on. So all we've done is we've changed the end of our word to indicate that it's an alcohol by putting OL on the end of it. Okay, so that's how we can these what we might call organic chemicals, these chemicals that contain carbon. We have these patterns. We also have, let me give you another group so we can get the same kind of idea. This functional group, which is rather nice, cool, COOH. I could write it like this, but it's not too useful to me. Usually you'll see it written like that. If I was to draw it out, it would be a carbon with a double bonded oxygen and an oxygen and a hydrogen stuck on the end. This is called a carboxylic acid group. So if I see that, I know that the chemical is a carboxylic acid. Okay, and we could actually use exactly the same kind of nomenclature here. So if we go back to what we did with the alcohols, except this time we say, scrap that one. Our simplest carboxylic acid would be that. Okay, it's one carbon. You can see my double bond oxygen, my OH there. That is actually called methanoic acid. Okay, it's got a common name of formic acid. That's actually what ants produce. So that would be. Write it like that. What's the next one? Well, it would be like that. Again, notice I haven't bothered putting my extra hydrogens in, and you might already have guessed this one is called ethanoic acid. Okay, so we've got the same patterns: meth, eth, meth, eth. The next one would be propanoic acid, and so on. Ethanoic acid is sometimes also called acetic acid, which is the acidic component of vinegar. Okay, this also comes up when you do respiration in A2. So it's just patterns again. So carboxyl groups, alcohol groups occasionally come up. This group, called an amine group, you might come across nitrogen with 2 hydrogens. We just keep coming across these common groups and they keep turning up. Now another bit that sometimes confuses people, another piece of paper, is ions and dissociation. If you take hopefully you remember that an ion is a charged particle or a charged atom or a charged molecule. So for example, sodium, when we come across it in biology, generally is in the form of an ion. It's a charged particle. It's lost an electron, so overall it has a positive charge. We might find it when we're dealing with salt, so sodium chloride, and the chlorine has a negative charge because it gains an electron. Okay. Normally we come across this, and this is something called dissociation. What this means is if we put salt, the solid salt, and we put it into water, it doesn't stay as separate sodium and chlorine joined together. What it does is it forms these ions, and these ions break away. They dissociate with each other, and they form these positive and negative ions. So you'll come across quite a lot of ions simply because in living things, you're mostly going to be talking about cells, which are mainly water, so any solutes in there are going to be dissolved in water, or the fluid surrounding cells, which again is mainly water. So a lot of these things will form ions, so you'll come across sodium quite a lot. The other ions you'll come across are things like potassium, which is also got a positive charge, calcium, which is involved in neurons and nerve transmission and releasing vesicles and a bit on your muscles as well. It actually loses 2 electrons, so it's got a 2+ charge. Okay, those are the 3 common ones you'll come across. You'll maybe see others as well. Carbon dioxide, when it's dissolved in water, will dissociate and form a weak acid. The hydrogen comes off and you end up with hydrogen ions. Okay, sometimes these are also called protons, and you'll be doing that, I think, in transport, where you're talking about carbon dioxide dissolved in the blood plasma. We get this carbonic acid ion. Okay. The thing that makes an acid is that it does this dissociation, if you like. So if we take hydrogen chloride, which is actually a gas, we dissolve it in water. It dissociates. We've got lots of these protons, these hydrogen ions floating around, and this is what makes it an acidic substance. So what we can actually do is to write this out as a little AQ after it, just like when you used to write solids, liquids and gases. So if we said solid carbon, that's carbon which is a solid. If we had mercury which is a liquid, you write that after it. If we had fluorine, for example, which is a gas, solids, liquids and gases, AQ means it's been dissolved in a liquid. And acids should always be written out in that way because it only becomes acidic when the hydrogen is able to dissociate and become an ion. So you might see this kind of stuff written quite a bit more now. Again, that's all it's referring to, that it's formed an ion because it's dissolved in liquid and these things have separated out.